Okay, welcome back to our afternoon session. Our next speaker is Hugo Parlier from University of Luxembourg. And the title of his talk is Quantifying Isospectral Finiteness.
Thank you. Thank you very much, Mahmoud, for the kind introduction. Thank you very much to the organizers for inviting me. I'm delighted, and it's a real honor to be here for Joseph. I really am. And everybody's been saying very nice things about Joseph, and I'm certainly not going to go against any of those things, but go in the same direction. He's been very supportive of me throughout my career, and I really appreciate that. And part of definitely part of this particular atmosphere here at CUNY that has one of the places where I really feel at home. And so thank you for that. And also, I'd like to point out that I feel somewhat responsible for being a representative of the Swiss school or the Swiss or the Swiss group. And in fact, I'm so much responsible for being part of the Swiss school that Bruno Colbois has entrusted me with a gift for you. So this is Bruno Colbois. Okay.
Good stuff.
And then I thought you might get sick if you drank all that without eating something, so I got you some Swiss chocolates, which my wife helped me choose. So, and then I felt guilty about not bringing something from Luxembourg, so I brought you this from the. It's a puzzle you can play with instead of listening to my phone. Okay. Anyways, so these are my notes. Did anybody, for those who were at Dennis Sullivan's talk, I thought I would try to get even smaller.
It's actually wrinkled.
But now I can't read them. All right, anyways, so I want to talk about the size of isospectral sets. So I think my title is Quantifying isospectral sets, or something. This is the brand new marker that you were telling me about?
One of those.
One of these. Okay. Anyway, so this is the basic setup. So we have, all right. For the sake of originality, I'll draw a genus 3 surface. So we have X is a hyperbolic surface. And you can associate to a hyperbolic surface the set of all of its lengths of closed geodesics. So you look for all closed geodesics on this surface. You look at all of their lengths, and you associate to this surface this set, which is the length spectrum of X. And what this is just a set of positive real numbers, L1 less or equal to L2, less or equal to L3, etc. And so just to be clear what I'm talking about, this is the set of lengths of, and then I'm going to add some, so they're closed geodesics. But I'm going to ask that they be primitive. So what I mean by primitive is that if you have a closed geodesic, then you can just run around that closed geodesic twice, and that gives you another closed geodesic. So I want to avoid doing that. So I want to avoid, these are all the geodesics that are primitive, so they're not iterates of some other closed geodesic. And I'm counting this with multiplicity. Okay, so if my surface has 17 geodesics of length 70, then I'm going to see 17 times in that. Okay, and some remarks about this set. It has different properties, this set of real numbers, and it's particular to discrete set. We're going to see specific versions of that later on. So there's only a finite number of lengths up into any given finite length. And what this really corresponds to is values of functions over a deformation space. So what I mean is this, is that x here lives in a moduli space which I'll call MG, which is the set of, so for genus G superior or equal to 2, this is the set of hyperbolic structures or hyperbolic metrics on a closed genus G surface, so hyperbolic closed genus G surfaces up to isometry. That's what I mean by the moduli space. So it's isometry classes of hyperbolic surfaces. And it lives in this space here. And when you move around in this moduli space, the lengths of these curves change. Right? And so you're moving around in this deformation space, the length of all of this changes, and you have this opposite direction, which is, suppose that you know the lengths of these geodesics, can you recuperate the actual surface that this corresponds to? So this is, in this particular setup, this is the inverse spectral question. So, to what extent do the lengths of closed geodesics determine the surface, and what do they determine, etc. So let me make, before giving you more information about that, let me make a few remarks. The first remark is that, suppose that I send, so remark 1 is that, or let's say remark, is that if I know if I have a length and I know what it corresponds to, so for each one of these, let's say so, suppose gamma is a closed curve, then it corresponds to, in its, so I'm on this surface here, and I have some closed curve that's non-trivial. There's a unique geodesic in this homotopy class. There's a unique geodesic. That's freely homotopic to this gamma. And why was I going to say that? Oh yeah, so now suppose that I know the homotopy class of the closed curve. So if I know the marked length, this is what I mean by marked length. So I know exactly not only their length, but what curves these correspond to. So marked lengths determine the surface. Okay, so if I actually know, so why is this? If I know what the homotopy classes of surfaces of the curves are, how do I figure out the surface? And this is sort of for many of you, a construction you've seen many times before, and the basic idea is this, is that you take a surface and you cut it along a certain number of curves into pairs of pants. When you cut along these, what you get is three-hole spheres. And the lengths of these three-hole spheres, to begin with, you have, each one of these has 3 lengths. So you have here length A, B, and C. Let's just look at that pair of pants. The lengths A, B, and C determine the geometry of the pair of pants. And sort of a standard trick is to see that is that you take this pair of pants and you cut along shortest paths between the boundaries. When you cut along that, you get 2 right-angled hexagons, like this, and that are this time hyperbolic. So these are hyperbolic hexagons. And hyperbolic hexagons are determined by 3 lengths. So 3 non-adjacent lengths, this one, and this one, determine exactly the isometry class of this hexagon. And so because I have sort of a front hexagon and a back hexagon, they share these 3 edges. So they're the same hexagon, which means that there's an isometry that brings the front to the back, and an involution that brings the back to the front. So that means that these two hexagons are the same. And in particular, that means that what I see here is A over 2. What I see here is B over 2. What I see here is C over 2. So retrospectively, if I knew the lengths of A, B, and C, I can figure out the geometry of this hexagon, and then I can figure out the geometry of this pair of pants. And so these lengths here, the length of these pants curves, tells me the metric outside of these blue curves. And so what you have to do is then figure out the length of these blue curves. Sorry, not the length of these blue curves. Suppose you know that. And then you have to figure out is how I've actually pasted these blue curves together. So if I have a blue curve and I've pasted a pair of pants like that to another pair of pants, to figure it out, I need more information. And for that, I can use, for instance, the length of this purple curve, which will give me some information about how this thing is pasted together. And in fact, I get all the information I need if I take two of them. Okay, so if I know the length of this purple curve, this green curve, then I know exactly how these things are pasted together. I mean, without getting into the details, what's important to know is why is that true? Is because the length of this purple curve, if I take a surface and I start twisting along this blue curve, the length of this purple curve is a convex function. Okay, so the length looks like this. And as most of my students don't know, that means that if I have this curve, then there's actually only two possible ways that this thing could have been pasted together. Okay, so I get two possible ways, and then I rule out one of the two by using the length of that green curve. Okay, so the lengths of all of these curves, so for each one of these pairs of, each one of these curves, I look at the length of these guys, and all of these lengths together, this finite set of lengths tells me exactly what the surface is. So I know exactly the information on the surface. Now, so that tells me, if I look at this sort of the marked spectrum, I'll call this sort of the marked length spectrum of X, which would be a little bit more than just the length spectrum, but it would be the length of, okay, so whatever the first curve is, length of alpha 1, less or equal to the length on X of alpha 2, etc. And this would be the marked length spectrum. This one tells me exactly what the surface is. And here's sort of and this is a sort of a funny fact. Okay, so I guess I should say result or something, or theorem. Something we proved roughly a little bit less than 10 years ago with Greg Mcshane, that you can do the following. So what I'm saying here is you know the length of alpha 1, you know the length of alpha 2, you know the length of et cetera, you know the length of everybody. But the theorem is that if you don't know the lengths, but you just know the order in which they are, you don't actually know what the lengths are, but you know which one comes first, which one comes second, which one comes third, etc. That determines a unique surface. Okay, so the orders, not the lengths themselves, determine a unique surface. Okay, so this is, I'm sort of writing this like this in quotes because I have to be clear about what I'm saying. But just knowing the orders of the different lengths of the homotopy classes gives you a unique surface, and in fact it gives you a unique surface in the larger space than moduli space. It gives you a unique surface in Teichmüller space. But okay. I'm just saying that you, right, okay.
So is that less in the order with the Pants decomposition? Or is that less information than you get, like you're given a Pants decomposition?
Right.
With the Morse.
Right, so to get the whole surface, you'll need a finite number of lengths, of marked lengths. So you need the lengths of the pants, and then you need the length of these transversals. And you have a finite number of lengths that is going to give you the whole surface. So you can't hope that the order of a finite number of lengths would determine the whole surface, because you're trying to, this is a large dimensional space, so you wouldn't have enough wiggle room. So you really need all the orders of the length. So you need this infinite amount of information.
That's a theorem.
Yeah, that's a theorem, yeah.
Right, because that's not there. You're saying that you definitely need all the information.
Yes, you definitely need all the information, absolutely. Yeah. And the reason is because you can deform a surface ever so slightly, such that the only ripple you see in the length spectrum is very, very, very far up. If you only needed a finite amount of information, then that would do it. Yeah. Anyway, so that's sort of a.
But
yeah.
any deformation of the surface will change some order.
That's exactly what we proved.
Okay. Right. Okay.
Yeah, exactly. No, that's equivalent.
Yeah. Right. Yeah.
Okay. All right. So that's, of course, I've gotten off track. I've done this to myself. Okay. So let me erase all this, and then. So the orders determine the surface. So in some sense, the markings determine the surface. And then, what about this question here and this inverse spectral question? And the answer is, so no. Okay, so the length spectrum does not determine surfaces, and there's a whole. All right. So let me give you a. I'm not going to give you a history, but let me just. Say the statements. So there exist isospectral sets or isospectral pairs of surfaces in every genus for genus at least 4. So what I mean here, so my definition is what's an isospectral set? So an isospectral set is a set of distinct surfaces, so non-isometric surfaces. Is an isospectral set Xn? Well, an isospectral set is these guys such that they have the same length spectrum, all of them, but they're not the same surface. So what I mean by not equal to is they're non-isometric. Okay, for as soon as I is different from J. And an isospectral pair is just an isospectral set with 2, and you find them in every genus starting with genus 4. It's not known whether they exist in genus 2 or 3. And so this is the result of many things. The first person to prove the existence of these was Marie-France Vigneras in the late 70s, early 80s. And then Tsunada came up with a more general technique, or a different technique, to prove the existence of such surfaces. And I'm not going to spend too much time on the history of it, but I'm going to write down some names. So Peter Bruser used his method, or adapted his method, to prove the existence of these. Carolyn Gordon and David Webb, who are here, proved together with Scott Wolpert some spectacular results using the Tsunada method, including planar domains. And then a result that's of interest to me here is Brooks, Gornet, and Gustafsson they showed the existence of large isospectral sets. Okay, and what I mean is n large, and they showed n on the order of n something like g to the power of some little some constant, it's explicit, times log of g. Okay, c is a positive constant. And so this is a function that, maybe it's not the usual function that we are used to look at, but this is a function that beats any polynomial, for instance, for g large enough. And anyway, so this is using Tsunada's method, and as far as we know, these are the largest isospectral sets that are known. And it should be pointed out that people like Ben Linovitz worked on the Vigneras method and showed that you can't get more than roughly g squared surfaces that are pairwise isospectral using that.
Is that for any g bigger than?
Well, for a sufficiently large g, this is
okay, all right.
Or alternatively, you can say there's a c uniform C positive such that
Yeah,
or whatever.
I couldn't remember.
Okay. So a lot of effort has gone into producing these surfaces that have this property. And I don't want to talk too much about that, but I want to talk about sort of the other direction.
Does this have to be a finite number? Could you have infinite number surfaces?
Good question. Great, that's exactly what I'm going to say. Okay, so very good question. And in the other direction, you can say a number of things about these isospectral sets. And here's one thing you could say. So, first of all, they're rare in some sense. So, Scott Wolpert showed that they live in a lower dimensional space. Isospectral sets from the moduli space has dimension 6g minus 6, and Scott Wolpert showed that they live in a lower dimensional space. And Mcshane Identities, that they're only a finite, they're always finite. So given x in a moduli space, there exists only finitely many y with this property.
So is this rare statement that there's like one subset that contains all possible pairs, or that for every one surface there's finite?
No, for every one surface,
There's a finite dimensional subset.
yes. So in that sense, there's infinitely many. So if you're
Right.
if you're allowing
Variation.
things, yeah, you can vary the structure of the surface.
Mm-hmm.
Right. Yeah. There's not only finitely many pairs in total. Okay. Yeah. Okay. And then Peter Boozer quantified this theorem. So let me write this up here. So this is a theorem of Boozer's. That isospectral sets are of size at most exponential 720 times g squared. Okay. So, I mean, this is an explicit quantification of the number of the size of these sets. And when I was a grad student, I looked at this. So, for those of you who have looked at Peter Boozer's book on the spectrum of surfaces, this is, I mean, a good part of the book is dedicated to proving this result, actually, if you think about it. About half of the book is dedicated to proving this result. And it doesn't appear anywhere else. He didn't publish this separately. This is only in the book. And I was very curious about this number as a grad student. Like, why, how on earth could he possibly have gotten to this number? Right? And so I looked at the result and whatever, and I was always very curious as to see, somehow that seemed like a very large number to me. Right? I mean, it probably is a very large number. If you take g equals 2, for instance, you're trying to prove that the answer is 1 for genus 2. Right, you're quite far from proving that it's 1. Right? You're exponential 720 times g squared. And let me tell you a little bit about the ingredients that go into Peter Boozer's proof. And I assume that some of this was done here at the grad center.
Yeah.
I mean, this is really typically the type of thing he was thinking about when he was around Stony Brook and when Peter was visiting here a lot. And so I assume some of this is here. And here's a very nice lemma that comes into the proof, which is sort of a useful lemma in any case. And the lemma says the following. So, if I have an x that lies in moduli space, so some hyperbolic surface, it has at most, what's the quantification? So g minus 1 times exponential L plus 6, closed geodesics, okay, primitive, of length at most large L. Okay, so this is an upper bound, a precise upper bound on the number of closed geodesics of length up until L that a surface can have. And let me just give you a brief idea why this is true. So here's the idea of proof. And this is very much, and all of this proof actually, this whole thing is very much in the style of Joseph's work in the sense of this relationship between the discrete and the continuous. And this is one of the examples of that. So what you do is you take a surface and you cover it with balls of radius 1. Okay, so you just cover the surface with balls of radius 1. So cover with balls of radius 1. And then you cover the surface with balls of radius 1, and how many balls do you need to cover it? Well, the surface is roughly area G, because it's a hyperbolic surface, so you need roughly G balls to do this. And then once you do that, what you do is you don't count geodesics, but you count geodesic loops that are based inside these balls. So each one of these balls has a center. So you have all these, you have roughly G balls. And then you count loops, so geodesic loops based in the centers of these balls. Okay, so if you take one of these balls and you look at now loops that are based in the center, so maybe there's a geodesic ball, and you want to count this. So you take this ball, you look at this, and now you look in the universal cover, H, and you want to count the number of loops that you have based in this. You look at all the images, all the iterates of this ball. And you have a bunch of copies of this ball. You let the group act, and you have a bunch of balls that lie like this. You want to count the balls that lie. How many balls can you have up until length? Well, you're only interested up until length L, or roughly L. So you look at something of radius roughly L here. Right? You look at a ball of radius L, and this ball of radius L is roughly, so we're in the hyperbolic plane, so the area grows exponentially, so this is roughly area equal to exponential L. And each one of these balls, they're all disjoint. So each one of these balls is roughly area 1. That means you have roughly exponential L balls. And I said we covered with balls of radius 1, we had roughly G balls, and that's exactly what this is. So this is basically the number of balls, and this is the growth area in the hyperbolic plane. So this is where this estimate is coming from. And something I'm putting under the table, and that at least Ara is curious about is, hold on, I'm lying when I say I'm covering this with balls of radius 1, because I can have surfaces that look really thin. So hyperbolic surfaces that have very, very short curves, they look like this, and this can be arbitrarily long. So if I really wanted to cover that with balls of length 1, I'd really need lots of balls here to cover that. So what I'm covering is actually the thick part of the surface, and I'm not covering the thin part of the surface. And so you have to watch out for that. But in this case, it works fine. But in all of this problem and in this theorem, one of the main difficulties is dealing with thin surfaces. That's one of the difficulties. And here's the first instance in which this appears. But that's okay, because closed geodesics have to go through the thick part, and so you can not worry about that actually in this proof. So that's the idea of this lemma. Okay. Here's another ingredient that comes into play. And again, we have this interplay between the discrete and the continuous, and that's that you count Pants decompositions. So you count topological types of Pants decompositions. Okay, so what do I mean? I mean, up to homeomorphism of the surface, how many different types of Pants decompositions can you have on a genus G surface? And for that, what you do is you think of a surface this. You take a Pants decomposition like this, and you dualize this Pants decomposition somehow. So you put a vertex for every pair of pants, and you join two pairs of pants if the two pairs of pants share an edge. And so what you get here is a graph like this. So that's one graph I could have gotten in genus 2. In genus 2, I could have gotten another type of graph if I had Pants decompositions look like this. Go. So these are the two graphs I can get in genus 2. So in genus 2, the answer is you can have at most 2 topological types of Pants decompositions. And these are the only 2 degree 3 regular graphs with 2 vertices. This one is. And so what this corresponds to is counting the number of cubic graphs, so degree 3 regular, degree 3 graphs, up to isomorphism. So that's how you count these, and then this turns out to be okay, so there's different bounds on this. This grows asymptotically like g to the power of 2g, but okay, this is certainly less than g to the power of 3g, for instance. Okay, so you have precise estimates on that. All right, so that's ingredient number 2, and then ingredient number 3 is something that Joseph has thought about. I know because he told me, and Peter told me too. And it's a theorem that's originally due to Bears. And then quantified by Boozer, and which is the following, that if you take x in mg, then it has a short Pants decomposition. So the theorem is that there exists a constant bg such that for all x, and this has a Pants decomposition of length less or equal to bg, this positive constant. And what I mean by that is the length of all the curves are less than this value, and Boozer's quantification is 20 times g, for instance. You can always find Pants decomposition length less than 20 times g, and this is called Boozer's constant. No, it's called Bears. You have to have a b to work on this. Okay. All right. And so how do these 3 things help for the theorem? Well, this is how you now set up the theorem, which is that we want to find isospectral sets of size at most this. Okay. So what am I going to do? So sort of step 1, these 3 ingredients. Okay, so theorem proof. Okay, so I choose a topological type of Pants decomposition. So I choose a Pants decomposition, topological. And I know that I'm looking at all surfaces that have this Pants decomposition as their minimal length Pants decomposition. And I know that I can attribute lengths to this, and there is some way of attributing lengths. How many lengths do I have to choose from? I'm given, what I have is, I have some length spectrum. Right, that's given. And I have to be able to attribute the lengths of the Pants decompositions to elements there. How many different choices do I have to make? I can use the lemma. So the lemma tells me that for each curve in this Pants decomposition, I have g minus 1 times exponential. So L in this case is going to be replaced by 20 times g plus 6 choices at most. Okay, for each curve. That's the number of closed geodesics up to that length. So I'm certainly not going to have any more choices than this, and I'm going to do this choice for each curve. So at most, okay, I'm going to be a little bit brutal in this estimate. I have at most, I do this for each curve, so I have at most, well, I have exactly 3g minus 3 curves in a Pants decomposition by topological computation, so I have at most this number of choices for the full Pants decomposition. Okay, and what does this number grow like? Well, this number grows like I have exponential to the power of g to the power of g. This is roughly exponential something times g squared. And that's exactly where this exponential something times g squared is coming from. And then this doesn't tell me the surface, of course. This just tells me the length of a Pansky composition. I made some choices. And then I have to deal with twisting, or what I was talking about earlier. So the pastings of pairs of pants. And so I have to decide how I'm pasting these pairs of pants together. And what I said before is to do that, you can use the length of these transversal curves. This one, maybe this one. And these lengths aren't very long if this length here isn't too long, isn't too short. So if this one's not too short, then if the surface is not too thin somewhere, then that's fine. I can use the length of these to proceed in the same way. These lengths are going to be quantifiably small enough so that I can choose them. But if this becomes very thin, I'm in trouble. So if this becomes really thin, then I have to use curves that get down in there and that are extremely long. Okay, so this is the thin parts. That becomes difficult. And you can do something, but I prefer to keep this on a need-to-know basis. Okay, so the thin parts again are part of the thing where this becomes interesting actually. And I'm going to talk to you about the thin parts, but in a completely different way from what Boozer does. Okay, right, and so there we go. So let me erase some things. Maybe just here, and then write down a theorem. So the theorem I'm going to write down is just an improvement on the cardinality. So isospectral sets are of size at most g to the power of some constant times g, and if you really want, you can take c to be 154. So again, for genus 2, this is not, we're not very close to 1 here. I mean, the point is, remember, the genus 2, we're trying to get to 1, and we're quite far from 1 in this case. Okay, and as one of my collaborators asked, is it clear that this function is actually smaller than that function? And it is. It is actually smaller than that. And this is a polynomial to the power g. And that over there is an exponential to the power of g. And as even some of my students know, exponential is larger than polynomial. Okay. Right, so they are, this is actually an improvement. Okay, but again, the idea is not so much the actual quantification, but more the things that go into showing something like this. Have I done something wrong?
No, that's easy.
Okay.
G, yeah, that's easy. G,
Okay.
yeah.
Okay. No, I know that those two functions I have done.
Yeah. No,
I spent about a month making sure before I wrote the paper. I gave it as homework problems for my students to make sure that it was true, and that decreased my confidence that this was true, and that was not a good idea. So let me tell you a little bit about the ingredients that go into this. I think they were confused, though, by why I always in calculus class use g as a variable. They don't understand why I do this. It's kind of long to explain it to them. All right. So what I want to talk about here is what I call curve and chain systems. Okay, so I don't like this pen. All right, so what's a curve and chain system? it's the following thing. So I have a surface. And I select a collection of simple closed geodesics that are disjoint, non-empty. I just gave a talk about this in France. You have to say non-empty. In France, it's important. So this is some collection of disjoint, simple closed geodesics. And then I cut along these simple closed geodesics, and I get a surface with boundary. So in my case, I get something like this. So I have genus 3, I cut along 2 curves, I get something that's genus 1, in this case. And now, what I do is I take a collection of arcs. Okay, and what these are disjoint arcs with their endpoints in the boundary. So simple arcs. So this is a set of A1 to A6G minus 6, as it turns out. So these are disjoint arcs with endpoints on oh, whoops, that's not true. This, and the arcs they all lie in this cut surface. Okay, so in my picture, I just take arcs that are disjoint, and until I can do this no more, because I'm always thinking of these as up to free homotopy. And for the arcs, it's free homotopy, where the homotopies are allowed to move along the boundary. Yeah, and so this is, believe it or not, such a set. And I do it this is a maximal set. So I do it so that I can't find any more arcs that are disjoint from the previous ones. And how do I know that that's the case? Because when I cut along these, what I'm going to get is, so I cut along this, and what I get is now a collection of hexagons. If you look carefully, these hexagons have the following property. They have exactly one side that's red, one of the arcs, and then they have a side that's a bit of the green, and then they have a side that's red, and then they have a side that's a bit of the green, and so forth. And because they're hexagons, I can't find any more arcs on this. Okay, so this, and the number of arcs here doesn't depend on the number of curves I began with. Okay, this is always 6G minus 6, just by an Euler characteristic argument. And so I have these arcs. And what happens is I want to make this geometric. So I can recuperate the geometry of the surface. That's what I'm interested in. And so what I do is I let the green curves be geodesic. So the green curves are now simple closed geodesics. And then the arcs, I let them be minimal length in their free homotopy class, and these become geodesic. And then this becomes right angles. And so what I've done geometrically, I've decomposed the surface into right-angled hexagons. And why have I done this? Because the lengths of the arcs, because of what I told you before, the lengths of the arcs determine the hexagons. So that means that the lengths of the arcs here, if I look at this here, so the length of A1 to the length of A6G minus 6 determine the surface, well, that I've cut along. So the surface where I've cut along is gamma. So it determines this cut surface, the surface with boundary. These lengths. And you should say to me, but we don't care about the length of arcs. You're trying to determine the surface using the length of closed geodesics. And I would say, yes, that's true. So, hence the following. So those are my curves, and then I get my called chains. And what is this? So I have these boundary curves. These are using the same colors as before. Sorry, so let me use the same colors as before. So these are the curves in gamma, and they're joined by an arc. So maybe like this. This is an arc. I want to find a length of I want to find a closed curve that I can associate to all of this. I'm going to use purple here. And what I do is I look at the epsilon neighborhood of this, what I've drawn. And this gives me a closed curve that I associate to this arc. So this is what I'll call gamma A. And this here is the arc A. Okay, does that make sense? So to get this, I'm thinking of this as a free homotopy class. So what I do is I have this boundary. So an arc joins two boundaries, possibly the same one. Right? And what I do is I go around the boundary, I follow A, I go around the boundary, I come back, and that gives me a free homotopy class. And so when I do that, I get this gamma A. There's another situation which I'm not drawing for you. So in this case, I get a simple curve. But sometimes I get something like this. Whoops. I did that on purpose. Okay, and then this is another situation which I can get, and then I just take this curve here. So maybe I'm doing exactly the same thing, only it's a trickier drawing. And here, I get this curve. That would be the curve gamma A. And these I call chains because I think of this as like, these are like, what do they call it on a bicycle? I should know this. This is preparation for a talk. Basic. Okay. The things on a bicycle that make the wheels go around, and you have a chain that goes around them. This is the chain that goes around them.
It's called a bicycle chain.
No, the chain, yeah, but what are these things? Gears. And then
Sprockets.
And then this is like once you hit a wall or something. And this is, or you're on a unicycle. Okay, that's the unicycle chain. Okay. Yes, that's what I call it. And so the point is, why am I talking to you about all this? Besides the fact that I'm happy I came up with these clever names, is because the lengths of all of these curves determine a surface somehow. So here's just sort of a fact of nature. The lengths of these gammas, so these are my curves, and the lengths of these chains, so these are, A belongs to this set of arcs. These determine the surface outside of this cut region.
Do you know the combinatorics? If you have the same length with different combinatorics, you get a different surface, no?
Right, yes. So these are marked.
Okay.
Yeah, these are marked. Yeah, you know the combinatorics. Okay, these are marked. And so this determines this, and then what that tells me is I know the surface outside of these green curves, and then to actually know the surface, I have to know how these are pasted together. So I need these extra parameters, which are basically these twist parameters, which I have to be able to show. So then I have to know how these things are pasted. So then these are. So you mark a point on this side, you mark a point on this side, and this is what you call a twist. Okay, so then if I just add plus twists, okay, then this determines, this tells me x in moduli space. Okay, so this is, the point is that this is what, right, so this is a set of curves, a set of marked lengths that tell me exactly what the point of moduli space is, modulo this twist, which we can deal with in similar ways as we were with Pence decompositions before. But yeah.
In that, the chain on the right with the arc going from the boundary to itself,
Right.
that curve has one intersection you have there?
Two.
Where's the other intersection?
Here and here. Two self-intersection curves.
Is that a well-described, I mean, is there more than one of those?
No, this is the only
How are you
topological situation.
How are you, only when it bounds is genus 1?
Only, no, it's only when the arc comes back and hits the same boundary.
Right, so how are you prescribing it?
How do I just, that's it, there's a definition for you.
So you
Take that picture.
So you follow.
No, I mean, so what I'm doing is this, is that the same procedure as before. I go around the boundary from this, I come here, I follow the red, and I go around the boundary and I come back. Exactly the same as before.
If you go the wrong way.
Why would I go the wrong way? I mean, you're right, I would go the wrong way when I'm trying to do it, but then...
But the other way is the
So you orient the boundary.
Yeah.
It's the same thing, actually. So this is why this is a unicycle chain. So if you turn this, both sides of the curve turn the thing. You're not trying to do two opposite things. You can actually make this chain run. There you go. I mean, not that it would matter if you couldn't, but okay. Anyway, yeah.
Yeah, sorry, to back up just a little bit. How did you pick your gammas to start with? What were the conditions?
Anything, any disjoint set of curves. Gamma can be a single curve, can be a whole pants decomposition.
So it doesn't matter whether the cut surface has topology or whether it's
absolutely not. No, it doesn't matter. But it does matter once. The only restriction I have is for the A is that they have to be disjoint from. They have to live inside this cut surface, except for the endpoints. Yeah. That's the only restriction I have.
So the cut surface can be disconnected.
Absolutely. It can be anything you want. In particular, it can be a pants decomposition. And sometimes I'm going to take it as a pants decomposition. Right. So why am I doing this? So it's worth cutting to the chase. For this, the reason I'm doing this is for the following reason, is that, okay, so here's a lemma. So any x that belongs to moduli space admits a curve and chain decomposition, a curve and chain system, large gamma, and let's say large gamma indexed by A, with the following lengths. So the lengths of all the gammas are less than 2 times the logarithm of 4g. All right. Okay, and then the length of all the chains are less than 8 times log 4g. So this is true for all the gamma in there, and this is true for all the A. So the chains are all of bounded length, where the bound now is logarithm in genus, and so are the curves. I mean, there's interesting questions in here that you could pursue further, but this is, and why does this help? Well, this helps because I'm counting, I only need to use curves up into a logarithmic distance, and when I take the exponential of logarithm, unlike what my students think, I get, so exponential of, for instance, 8 times log 4g, and they're always confused when I do things like this, so I'm counting all the curves up into this length. This is less or equal than, okay, I have no idea, but it's less or equal to 10 to the power of 100 times g to the power of 8. Okay, so it's polynomial in g. That's the point. And I get g to the power of 8. So when I'm using this lemma for counting curves, all of a sudden I've gone from an exponential to a polynomial, right? Which is exactly what I'm hoping for. Okay, so that's ingredient number 1 that goes into trying to prove this. And ingredient number 2 is something completely different. And this is dealing with thin surfaces. So let me just give you one idea of what comes into this. And this is thin surfaces. And I'm going to talk to you about something that seems completely unrelated, and of course in some sense it is. But okay, so this is Mcshane identities. And so what are these? So if you haven't paid attention to anything up until now, that's fine. This is completely different. So this is a theorem by Mcshane, as the name suggests, that says the following. And so I'm going to change context. I'm going to take a surface that has genus 1 and that has a cusp. So this is not at all the context I was in before. So I take a genus 1 hyperbolic surface with a cusp. And what Greg Mcshane proved is the following, is that on this surface I have a bunch of simple closed geodesics. An infinite number of simple closed geodesics. And what he proved was that if I take the following infinite sum over all simple closed geodesics, I take 2 divided by exponential length of gamma, and I do plus 1. I add up all these infinite terms, I always get 1. Okay, so what's remarkable about this equation here is that on the left side, you have an infinite number of terms. When you move there's lots of hyperbolic metrics that have this property. You can move this hyperbolic matrix. Again, all the lengths move, but their infinite sum does not. This remains constant. And you can generalize this in different ways, and here's one generalization that's due to Mcshane again. So now I have just one cusp. You can do this with more cusps, but okay, you have one cusp surface, and you do the following thing. Okay. You sum over the following thing. You take an embedded pair of pants that has two boundary curves that are simple closed curves like this. It's embedded, so they have to be simple. Okay, and one boundary curve that's the cusp. And you do this for all possible embedded pairs of pants. And you sum like this over all possible embedded pairs of pants. And you take more or less the same sums. You take exponential length of alpha plus length of beta. Those are the two boundary curves, and you divide that by 2. And you do plus 1, and then this is always equal to 1. Okay, so it took him a while to get from here to here for obvious reasons. He wanted to find a sum that was sum over all simple closed geodesics, but that's not the right way of thinking of it. It's actually this. Okay. And then you can generalize this, and this is to surfaces that have boundary. Okay, so here's a surface with boundary, and let's call this boundary, I have no idea, gamma. Okay, like that. And I can do the same thing. So I'm interested in surface with boundary because remember, I'm trying to think of these cut surfaces that I'm getting. So let's just say I have one single boundary. I cut along it. I have something like this. And here, so this theorem here is due to Mirzakhani. And independently by Serapio-Tan, Wang, and Zhang, that if you take the sum, the same sum, and I'm not going to write down, they have a less explicit function that depends on the length of alpha, the length of beta, and the length of gamma. And I sum over all these pairs of pants. So the summands are all the same. Again, I get 1. And, okay, so this is, and this really is a generalization of this one because you can limit this one to this situation and so on and so forth. And I just want to say one thing about that function. Is that the function satisfies, it's a 3-variable function, and it satisfies this, exponential x plus y divided by 2. So I take 1 over exponential x plus y divided by 2, and that function is greater than that. And this doesn't depend on the third variable. It's a universal statement. And what does this tell us? This tells me as a corollary that there are most exponential L embedded pairs of pants like that. Okay, so why is that? Because each one of L is a positive.
Just okay.
And so why does this tell me? Because each one of this is like, you think of this as a probability measure on the set of pairs of pants that are like this. Each one of them contributes something. And if they all contributed more than exponential L, 1 over exponential L, then this would be strictly greater than 1. So it's a consequence of this. And this helps us because this helps us deal with thin surfaces because these curves become very, very long, but they live in pants that are restricted here. These lengths become restricted. And so you have to find a way of, instead of counting the number of curves that are very, very long, you count embedded pants, and you count the curves using these embedded pants. Okay, I'm going to stop here. Thank you very much.
Are there any questions?
Can you say what that second sum is?
This one here?
Yeah.
Yeah.
Summed over?
So,
Yeah.
right. So
Yeah.
there's different ways you can think of this sum. One way is I want to look at all homotopy, pairs of homotopy classes, alpha and beta, that bound a pair of pants with this here. So if I fix alpha, for instance, I still have an infinite number of these. Another way of thinking of this is I take this picture, and now I let a homeomorphism of the surface act, and I look at the image. And so then I get a new pair of pants. Alpha goes to some other curve, beta goes to some other curve, maybe the same one if the homeomorphism fixes it. And I let all homeomorphisms of the surface act on this. And I sum over that. So you can think of this as a sum over the mapping class group, so the set of homeomorphisms of the surface as well. And in fact, so like a corollary of Mirzakhani's stuff for the counting things is that this grows like a polynomial. The number of these grow like a polynomial, an explicit polynomial, where the exponent of the polynomial depends only on the topology of the surface. Yeah.
What's your estimate on the best possible?
Right. Okay, so that's a good question. That's a good question. So,
I should know because the problem.
right. So my estimate is that I'm rooting for this one because then my upper bound is correct. No, I really don't know. I mean, I don't know, but I say a couple things. You can ask the same question for graphs.
Yeah, right.
Right? And for graphs, the answer is something like this,
Yeah.
where you replace the genus by, you take regular graphs, and you replace the genus by the number of vertices, and the answer is something like that. That's for instance, triangular, 7 regular, whatever you want, right? So the answer is something like that. The other thing is that as soon as you have something that's combinatorial, any type of combinatorial counting that comes into it, then any upper bound where you use a combinatorial counting thing, you're going to have something g to the power of something times g. This is the same thing as the number of triangulations on a surface, the number of ways of decomposing this thing. So if you have any type of combinatorial counting that comes into play, the number of covers of a surface also goes like this. I mean, it's often g to the power of 2g. The volume of moduli space goes like this. And so unless something completely different comes into play, then I'd expect more g to the power of something times g. But I really don't know. Of course. Otherwise I'd say so.
Any other questions?
How did they get the g to the log g lower bound?
Oh, it's using Sonata's method and using covering techniques, and it's difficult. I mean, for me.
Any others? Okay, let's turn to our speaker again.